Okay, this is part 2 of the lectures on simple circuits from chapter 26. This covers the basics of parallel and series circuits. That is, what happens when you put resistors in series and resistors in parallel. So the first thing that we take a look at is what is called equivalent resistance. All right, so let me begin with a description here of, first of all, parallel circuits. So let's say, for example, that I have a battery, like so. We'll ignore the internal resistance and the EMF for now. And then I have right here a resistor, call it R1. And then secondly, right here, a second resistor in parallel, call it R2. This right here is the voltage V. Now, as I mentioned earlier back in chapter 25, whenever you draw a straight line on a circuit diagram, you think of that as an equipotential surface. So then therefore, as the current flows, we think of this right here as an equipotential surface, and this right here is an equipotential surface. This then means that the voltage V of the battery is the same as the voltage across this resistor R1. It's the same as the voltage across this resistor R2. So here's a voltage V, and then here's a voltage V. Okay, and then the current flows like so, I, and then it reaches right here at junction. When it reaches a junction, it then splits into two. We have a current flowing in this direction now, call it I1, and a current flowing in this direction, I2. This right here, by the way, is the first of what is referred to as Kirchhoff's laws or Kirchhoff's rules when analyzing circuits. This is called Junction Rule. Okay, for Junction Rule, very simply, the amount of current that flows into a junction is the same as the total amount of current that flows out of the junction. If the two values were different from one another, that would ultimately be a violation of conservation of energy. So in other words, I is equal to I1 plus I2. Okay, so now using Ohm's law, I'm going to go ahead and rewrite this expression here to come up with a description of equivalent resistance. In other words, right here, these resistors rather in parallel, they behave as a single resistor. We're then going to go ahead and find that equivalent resistance. We'll use Ohm's law to do so. So here on the left-hand side, we have the current I. Think of this right here as being equal to the voltage V, and then divided by what we're trying to find, which is the equivalent resistance. So, and then for current I1, okay, I1 is passing through this resistor right here. Once again, the voltage across that resistor is the same value as V. Therefore, using Ohm's law, we'll write the current I1 as V over R1. So, and then similarly for the current I2, we'll go ahead and write that as the same V and then divided by R2. And then, of course, all the V's just cancel out. So then therefore you end up with this relationship here that then describes the equivalent resistance. It's a 1 over R relationship. Compare this to the capacitance in parallel calculation from chapter 24, the equivalent capacitance. When you have capacitors in parallel, it's add them all together to get the equivalent capacitance. Here, however, when you have resistors in parallel, then it's a 1 over relationship like so. Okay, now let me show you the advantage here briefly of a parallel circuit by means of this light bulb demonstration that I have right here. I have two light bulbs here and they're all hooked up to the same circuit. I'm just going to plug it into the wall socket in just a moment. And then by means of this switch, I can switch back and forth between parallel and series. So right now I have it hooked up in parallel. And I'll go ahead and plug them in like so, and then both light bulbs light up. However, I can go ahead and unscrew one of the light bulbs. When I do, I basically broke, say, this portion of the circuit, but current is still flowing through this portion of the circuit here, and the other light bulb then stays lit. I can do that backwards as well by doing it like so. However, the more light bulbs that you have lit up in parallel, the more current that you begin to draw from the battery itself. You'll see what happens if you draw too much current in a numerical example a little bit later on. Okay, next, let me go ahead and show you the basics here of a series circuit. What happens if you have two resistors in series? The first thing we do is we calculate the equivalent resistance. Okay, so right here, once again, is my battery with voltage V. And now I've got a resistor here and a second resistor here like so. So here's R1 and here's R2. Okay, once again, you have a current I that is flowing through the circuit. We're going to have a potential difference here across this resistor, call it V1, and a potential difference across this resistor here, call it V2. Okay, the sum of the two, V1 plus V2, has to be the same as the voltage V. Once again, think of it in terms of equipotential surfaces. Right here is an equipotential surface. Right here is an equipotential surface. So then therefore, the overall potential difference between these 2 points is the same as the difference between these 2 points, which is that of the battery, that's the voltage V. So then therefore, the voltage V is equal to V1 plus V2. Go ahead and replace these V's here now with I times R from Ohm's law. So on the left-hand side, this is I times what we're trying to find now, the equivalent resistance. This is then I times R1 plus I times R2, and then all the currents I cancel out. So then therefore, the equivalent resistance is R1 plus R2, like so. So you add up the resistors then in order to ultimately calculate the equivalent resistance for a series circuit. Okay, compare this expression here to the equivalent capacitance calculation from chapter 24 for capacitors in series. If you make that comparison back in chapter 24, it was the 1/over relationship to find equivalent capacitance. So you end up with two similar equations here for equivalent resistance as you do for equivalent capacitance. Well, you'll notice that they're backwards from each other. Sometimes this is a little bit difficult to remember. So for a series circuit involving resistors, just add them up. For a series circuit involving capacitors, it's the 1/over relationship. On the top board, for a parallel circuit, for equivalent resistance, is the 1/over relationship. However, back in chapter 24, for capacitors in parallel, it was add them all together to get the equivalent capacitance. Once again, it's a little bit tricky to get the two backwards. Okay, now compare the two expressions to each other here for equivalent resistance for, first of all, parallel, and then secondly, for series. With respect to the top expression, the more branches that you have to the circuit, the more paths that you have for the current to flow. So then therefore the resistance goes down when you do. So the equivalent resistance, if we were to calculate it, is going to be less than the resistances R1 and R2 added together, for example. However, down here on the bottom board, with respect to a series circuit, if you have, for example, more resistors here in series, then you're basically making it harder and harder for the current to flow. So then therefore the equivalent resistance is going to be greater than the values of R1 and R2. That's obvious from this expression here. Okay? Okay, let me go ahead and conclude that as part 2.